There you go. Okay, so this is first question out of assignment 7. So we have assembly line, 17 tasks, okay, and the longest time is going to take 2.4, and total time for all tasks is 18 minutes. And the line will operate for 450 minutes. So that's the operating time per day. So based on the formula given from the textbook, so by the way, we're going to work on the cycle time and output rate. Okay, so when it comes to the cycle time, it talks about maximum time allowed for each workstation to produce, desired output. Okay, so we can say how fast things move. That's the time we're going to measure. So to calculate cycle time, so you need to have operating time per day. In this example, we have 450 minutes. Then denominator we have is desired output rate. Okay, in this example, we have 90. Okay, this is just example. Okay, so this is example. It's not related to actually this question. So I'll give you some idea what exactly we're talking about cycle time. So here's another, not related to this first question, but it's different example. So a plant operates 450 minutes per day, then we want to produce 90 phones. So that's the output, desired output. So our cycle time is take total time per day and divide by the number of output. So 9 minutes, that's our cycle time per phone to be produced. So we're going to have to spend only 5 minutes or less, okay, to meet this goal, which is 90 cellular phones per day. Okay, so that's kind of example. So to begin with our actual problem 1, so what's the minimum cycle time, which is given 2.4 right here, and maximum cycle time is given again, there will be 18 minutes total. Okay. Then what's the range of output for the line? So we are calculating output. So there you go. That's what we're going to use. So we're going to have those 450 minutes divided by cycle time that we have here. One is 2.4. The other is 18 minutes. So that we have 187 units, and the other range is 25 units in terms of the highest and lowest level of the product line. Okay, then moving on. Then how many workstations we're going to need for this particular case? So to find minimum number of workstation, again, is given, from the formula. That's the total task time divided by cycle time. Okay, so total task time is 18 minutes and divided by 2.4 minutes. Then we'll have the 7.5 approximately, so that must have 8 workstations to satisfy the total task time, right? Okay, there's another kind of variation from this formulas. So to produce 125 minutes, then what is the cycle time, right? So using cycle time formula, this time 125 instead of, was that 18 or other numbers, right? So just put it into formula, then we get 3.6 minutes per unit in this example. Then last one is, so what's the potential output, and if the cycle time now is different, 9 minutes and 15 minutes, then again, put it into same formula, then we're going to have potential output. Right here, so using this formula. Then we'll have that units for 9 minutes cycle time and 15 minutes cycle time. Any question about first one? So main thing is just understanding cycle time and output rates, and then plug into formula. Give me 1 minute. Okay, question number 2. So here's the diagram of workflow. That's what they call precedence diagram that tell you what kind of task will happen, something else has happened, right? So it'll help you plan in the right order, okay? So the workflow goes that way, following the arrow, right? So the time, I think a little bit too small. The number shows the time take to complete the tasks, okay? Then we have those flow goes to all the way to H, starting from A. But task B can take either D or E. And from there you can go all the way to H, all right? So this is tell us how those work will flow in what kind of order, so that we can calculate what they call positional weight. So positional weight is in each position, then you add whatever test time for your task plus the time take for the remaining of the tasks. So what they call all times downstream. For example, for A's positional weight, then you need to add 1.4 plus 0.5, right? Then you add 0.6, 0.5, 0.5. And here we go. That's how you're going to show. So you're ending up having 6.0 because you're going to end up adding all 7 eventually. That's 1, 2, 3, 4, 5, 6, 7. Okay. Starting from B, you're going to have 6, right? 6 tasks will be added up. So that's why you have a 4.6 in terms of positional weight. C, for the positional weight, you have only 2 tasks following task C. So you add those numbers, then you have 1.6. Okay. So you just keep adding it just like that, and that shows positional weight. Okay, so that's the number you come up with. All right, then we need to determine cycle time, right? So how long it's going to take to produce each unit. In this example, we have numbers are given in terms of 60 minutes, right? 60 minutes for the period. Then we have the output. Desired output is 33 and 1/3 unit. So if you take that and put into the formula, 1.8 minutes per unit. So you need to have at least, you need to have a 1.8 minute or less to produce in that particular position, right? Then what's the total task time, which is given? So you add them up, all those numbers, which is number of minutes, then you have 6 minutes exact. So that's the total task time. All right, so we have those two numbers, cycle time, total task time. Then you put it into again minimum task workstation, number of workstation for this particular case. That will be 6 over 1.8. Then you have 3.33. 3.33 is approximately, you need 4 station, but not 3 station, right? Because it's too small. So you need to have at least 4 station instead of 3. Okay. So that's to kind of, establish your base numbers to move on to next step, which will calculate and which will consist what workstation would which tasks. So now we're going to assign each of those workstation which task you'll be assigned. You're going to assign A and B into workstation number 1, or C and D to workstation number 2, and things like that. So that's what we're going to work on next. Okay. So here we go again. I think I should make it bigger. So that's our diagram. And the first, let me see, where's the question? Oh, there you go. Question is, we're going to find out each station, for each station, which task will belong. So we'll do it for most following tasks, meaning that, whichever task has the highest number of following tasks will go through there. So for example, you go starting from A, you go B, then to determine which way you're going to go, you'll see which node has the, largest number of following tasks. In this example, either C or E has the highest numbers, right? Following tasks. Because if you go to C, you have still 1, 2, 3. If you go this way, E, you have 1, 2, 3 same. So you have tie. So that's what it means by tiebreaker. So if there's a tie like this with the same number of following tasks, then you go with greatest positional weight. So you calculate or you look up the larger positional weight for C or E. So if you look at number here, C between C or E, then if you go C, positional weight is 1.6, right? If you add them up. If you look at this way, which is E, you got, what is it, 1.8, 2.3. So the position E has the higher positional weight. So you want to go that way rather than, task C. So that's what I mean by tiebreaker, then you choose the greatest positional weight. So that's how you're going to approach this question. Okay. So here we go. So I come up with this table. Look a little bit, confusing in the first place, but you'll understand how I did it. But it's up to you. You can come up with your own way, because it's more like heuristics rather than, mathematical formula. Because probably AI can do it mathematically, but I mean, to me, it's not that simple because you need to go through different route anytime you have a tie and so forth. So anyway, so from workstation 1, so starting from A, right? So again, each station you have only 1.8 minutes. Okay, so here we go. The eligible task for starting point is A because you're starting from A. So there's a will fit. Yeah, A will fit. That's what it means. Then what's the task time assigned? 1.4, which is given. Then how many minutes remaining? Since 1.4 minute has been assigned, remaining 0.4. That's 1.8 minus 1.4. Okay. And if there's idle time, then you show the idle time. Okay, so that's how we're going to start. So start with A, then 1.4 minutes given, then remaining minutes is 0.4. Then we're going to move to task B. So task B is 0.5. So 0.5 is bigger than 0.4, right? So we cannot, put it task B to station 1. So we have to let it just sit there for 0.4 minutes. So that's what I mean by 0.4 in idle column. And moving on, station 2, workstation 2. So which task we're gonna put it into station 2? So obviously B will be the first choice. So 0.5 minutes has been spent. So the remaining minutes, 1.3. Now we look for C, D, E, right? We have 3 choices. So the rule is the largest remaining tasks, right? So there's a tie, C and E with the 3, right? C has 3, E has 3 remaining tasks. Because a tie, we have to look for the largest positional weight, which is C. It's a C or E? Which is E, I'm sorry, which is E with 2.3 versus 1.6 for C. So that's why we take E on this step. So remaining time will be 0.5. Okay. So next eligible task will be either C or D, right? These two, C or D. Okay. Why, if you go this way, you have only 1 remaining. So you need to go C or D because 2 remaining tasks. So either 0.6, 0.7 will fit into 0.5. No, they are not, right? Wait a minute. Are we, oh, I'm sorry. Yeah, right here. 0.5, yeah. I was looking at station 3 already. So 0.5. So, 0.6, 0.7 is bigger than 0.5. So we have to, put it into idle. We cannot satisfy C or D. So C or D will go to station 3. In station 3, again, 1.8 minutes is refreshed. Then you put it either C or D. But we're going to choose D because of higher positional weight with, 2.2. We go that way, right? Versus 1.6. Okay. So that's how we're going to move this thing along, right? I think you get the point, hopefully. If you have any questions, let me know for this set.
I guess in this case, we're just taking the time it takes to complete a task. Like what happens in a case of products that are interdependent? Like we have to finish one task before we do the next. Or in this case, it doesn't apply.
It doesn't apply. We just, put it into the station together in terms of how many remaining tasks you have. So
I see. Okay.
Yeah, of course, this is kind of, put it in a different category because you have to think about all other variables. Of course, you can come up with different variables, different circumstances for workstation and all that, but this kind of assume with only number of minutes with, number of remaining tasks.
Okay.
All right. And the other question is asking this time the order of tasks will be depending on greatest positional weight, not the remaining number of tasks. Okay. So let's see how this time will be different in terms of which tasks will be assigned each station. By the way, first example, for the first station, we have A, station 2, B and E, station 3, D, C, F, then station 4, G and H are assigned. Okay. Now we're going to take a look, this case and see how, this assignment can be different from. All right. So again, we start from A, go through B, then from B, we're going to look at the greatest positional weight, right? So starting from A, then remaining 0.4, but again, same thing like the other case, we have to put it into idle because 0.4 is smaller than 0.5 minutes for task B. So starting station 2, and we're going to put task B first of all, then remaining 1.3, then we look for either C, D, E, and we need to pick up the largest positional weight. That will be E, right? Because again, that will be 2.3 in terms of positional weight. C and D is much smaller than 2.3. Okay, so we assign E, then what we have is 0.5. So either C or D is larger than 0.5, so we have to put it into idle again, right? Then station 3, look for eligible tasks, which is C and D, compare C and D in terms of positional weight, and D is larger because that's like 2.2 versus 1.6 for station C. Task C. Okay, so that's why we have it here. Right here. Then we have 1.1 minutes left. Then we're going to compare C and G. C which has a greater position weight. Obviously, C, because that's 1.6, and G has 1.5. Okay. Then move on. Then ironically, I think we have the same answer, is it not? Yeah, A, B, E, D, C, F, G, H. So that's how we come up with station 1A, station 2, station 3, station 4 with different tasks. Any question about this? So it's more like a, some kind of puzzle, but again, we need to follow again the rules that is given. So, all right. Then asking about line efficiency. Okay. So whether this line that we have it here is efficient or not. So the formula is given is total task time, which is 6 minutes. And the number of workstation we come up with is 4 times cycle time 1.8. That would be numerator, denominator. Then you divide by, of course, 7.2. Then you got 0.833, which is 83, approximately 83%. Meaning that about 83% of time has been used for real work. So the time well spent in terms of 83%. So it's like a 17% is like a idle time. So to improve the efficiency, I think it's pretty obvious that you reduce number of stations, right? Then you'll achieve higher percentage. Okay, so any question about this one? The workstation problem? All right, moving on. Next one is more of department arrange problem, okay? That's what they call in operations management, department arrangement problem. It's more of heuristics again. Heuristics is more like there's no mathematical formula or mathematical equations to prove or to test. So more of applying rule of thumb or common sense. So you have to try and see what happens, like trial and error, more of time. Some people say it's more like a puzzle, but it's not like a puzzle because most of the time puzzle has the correct answer, but heuristics problems can have multiple answers. Okay, so that's the difference between heuristics and puzzles, I believe. Okay, here we go. We have a 6 department. We're trying to put it into slot, 2x3 grid. And there's some conditions. Once again, 6 department. And 1 and 2 must be close. 2 and 5 department must be close together. 5 and 6 must be linked. However, 3 and 1, 3 and 2 must not be close. So I think a better way is just kind of visually put it into this problem. So you can put it into, you can just write it on, draw a diagram or figure just like that. Like here I put it in 1, 2, 5, 6 because that's what we have, 1, 2, 2, 5, 5, 6. So I put it and connect them and then see what we have in for not to be close, which is 3 and 1. So 3 must not be close to 1. So either put it into near the 2 or 5 or 6. Right? Same thing. Between 3 and 2 must not be close. So just try and put it into like this. So that's what I have. So most frequently appear numbers here 2 and 5. So I put it like a corner. Right? So 2 is here, 5 is here. So I put, since 2 is here, I put a 1 above. And because 5 and 6 need to be connected, 6 is here. And then remaining numbers are 3 and 4. So 3 and 1 should not be close. So 3 is far away from 1, then 4 doesn't matter because 4 did not mention over here. So that's the one way to do it, right? Again, this is not the only answer. You can put it other way, like I think you put it 2 over here, same thing, 5 over there, right? Then you put 6 Oops. Then you can put 1 above and 4 and 3. I think it's the same thing, right? Well, that's kind of mirror image, right? So that's another way. I think we can, that's a third way, I guess. I didn't have time for that, option, but this is so far I thought about. So anybody found third way? Well, there is third way. I'm not sure. So, okay. If you don't have any questions, moving on. Okay, so similar to this the department arrange problem, that's kind of interesting diagram over here, what they call activity relationship chart. This is pretty practical chart. So that again, we're going to place department, one together, but there's more conditions here. Okay, conditions are here in terms of a different letter. A is absolutely important to be close. E is especially important, so it's the next level. I is somewhat important. O kind of middle of the road. U is unimportant. X undesirable, so must not be linked or close. So those are the conditions we need to satisfy. And then we need to read this diagram. So to be able to find between two departments, you need to read like that. So it goes like column, row, or row, column. It's kind of interesting way to put it. But anyway, you go cross here, then you moving to this way, then you have department 3. So that's the slot you have to look for between department 1 and 3. So between department 1 and 3 is A, right? So it must be close. And department 1 to 4 is E. It's somewhat important, right? Department 1 and 5 is U, unimportant. Department 1 and 7 is very important. Department 1 and 8 is again most important. So that's how you're going to read it. Okay. Some are kind of repeated down here because of, the grade. So you'll figure it out. Any question about this diagram?
It just makes me wonder how this is used. Is it to design the office at the construction stage or arrange?
So that you can put it into slot like this, just make a simple assumption. So which department put which slot? Just like that. You have 9 slots. So having these conditions in terms of how important, put those departments together, then you can arrange it just like that. So that's why we're going to figure it out. So again, this is heuristics. It's not really like a scientific way of figure things, but that often used in the real places. Because kind of easy to use. So you figure what department have A links, which is most important, and which department has X link, which is most unimportant, I guess, or must not be together, right? Then E links and I links. Okay. So why we are doing this way? With this, it's almost impossible to come up with idea, unless you're a genius, right? Some genius people can figure out of this diagram, but in order to move on, make it a little bit easier, so we can put it into this, table first. Then we go from there and figure where we're going to put which link. One condition is department 5 must be at the bottom. Where is that located? I think they have said so. Yeah, right here. Place department 5 in the lower left corner. Okay, so that's the one condition. Kind of give you a hint, right? So that's why you put it 5. Then you go from there. So one way you can do is just look at the number show up most frequently from A link, because that's the most important links. So like 2, 1, 2, 3, 2 appears 3 times. 5 appears 3 times. 7 appears 1, 2, 3, 4, 5, 6. So 7 appears 6 times. That's the highest number. So that's why I put it into 7. So of course that's easier to connect if you have a 7 in the middle, right? So that's the kind of idea. That's not my idea, but that's what people do, So then you go from there. And there's no actually, afterwards, after this, after you put into the 7, that's up to you, how you're going to approach. You want to approach from, looking at X link that must not be linked, or you can look up A link, which must be closed. Either way you can start and see which way is the better. So eventually you're going to have this kind of slots. So, this is again heuristics rather than algorithms or any mathematical problem. But in terms of real world, this is really happening and they have been using it, but I don't think we use a lot lately because we have other technologies available, just like AI and other methods we can use. But for our class purpose, we're gonna think we may have these questions like quiz or tests. But it looks like 9 slot 3 by 3 is a little bit too many. Could be 2 by 6, something like that. 2 by 3. So any questions at all?
Nope, all good here.
Okay then. That's all I have, and have a nice weekend.
Okay, thank you, you too.
Okay.
Bye-bye.